Okay. Now we have the result from the appendix. It's rather long. I will just refer to you. You can look in the paper. The result on the in the appendix of the paper published in TSAMP deals with well-posedness and exponential decay of the boundary layer problem, of course more general than this one. So unfortunately we could not just refer to the known result from the literature. We have to consider, I will write this general problem. So in the appendix in TSAMP, one can find the result on the boundary layer problem, which of course can be used not just in this situation, but for other situations as well. So the result on well-posedness and exponential decay is derived for the following system. Domain is this one, the infinite, semi-infinite stripe. So some constant vector on holes. No slip on the solid part of the porous boundary. And of course the periodicity condition. And in the appendix, we have the result on well-posedness of this problem. Of course, we have to assume additional assumption on this right-hand side function, essentially that its mean value equals to 0. And the important thing is that it can be generalized on a 3D case. Of course, by taking into account the difficulties. So if you compare the system phi with this one, then you can see that this one is of this type. And all the following ones, so all the problems imposed for the auxiliary functions, which we use to define the next order approximation, will essentially derive system like this. That's why this result is very important, and as I said before, it can be used in a different situation, because what do we have here? We have here a Stokes system with the right-hand side not necessarily equal to 0. We have a divergence equation with, again, right-hand side. Why this is important? Because for the next order approximation, we will have something on the right-hand side. And we have on the porous, on the whole part of the porous boundary, we have imposed the normal stress. Well, this D is any vector. So in the appendix it is proved that there exists a weak solution. It is also proved that the corresponding weak solution exponentially decay towards a constant. And essentially, using this result, we now go back to this problem here. So the result from appendix, what I'm going to erase now, I will erase this problem, I'm sorry, because I need to keep these equations. Okay, so theorem 3 from appendix guarantees that problem 5.1 to 5.4, so this, and this, has a solution exponentially decaying towards constants, towards some constants. Let us denote them by W k infinity. For any choice of tau k, okay? This is D in the appendix. Essentially D is this, yeah? Okay? And the idea choose these constants tau k such that this 1 is equal to a canonic vector. So in a way that the velocity part of the auxiliary problem stabilizes towards this constant, while the pressure part exponentially vanishes. Maybe you can put here like this. Of course, as this one goes to infinity. And theorem 3 also proves that such constants exist. So this is the part of the assertion of this. That they have positive sign as well. So essentially from theorem 3 we deduce the existence of the following triple. So when consider this all together with this condition at the infinity, it is not essentially overposed because this is also the part of the problem. So essentially we are looking for this triple. And the result guarantees that this triple exists. And it can be proved, you can see for the details in the appendix, that it is a positive sign, which is important for the purpose of the analysis in the second. And now, by choosing these auxiliary functions, wk, to stabilize towards this unit vector, what do we observe from the ansatz for the zero-order approximation? So, outside note, outside of the boundary layer, we essentially have what? We have that our zero-order approximation, which will turn out to be our effective velocity that we are seeking for, is essentially outside of the boundary layer equal to this. While for the pressure, excuse me, outside of the boundary layer, due to the fact that we picked that the stabilizing constant is equal to 0, is 0. And this is our effective velocity. Okay? Effective velocity for which we need to derive first the boundary condition, in particular the one on the porous boundary, and the second one, the effective equation. The boundary condition for the effective velocity and effective pressure. We still do not have effective pressure. Where will effective pressure appear? It will appear as a part of the solution for the U1. So the effective boundary condition, we will deduce it from the next order problem by taking into account the dynamic boundary condition. And then, from the last problem, this one, we will deduce the effective equation satisfied by our effective velocity and pressure. Okay, now we know how the solution for U0 and Q to the minus 1 is given. Now we have to, excuse me, compute this one, because it is given in this expression. We have to compute this one. We have to compute this one, and derive the problem for U1 Q0. But I will leave that for our next lecture, okay? For now, it is quite enough. Thank you very much. Do you have any questions? If not, we are finished for today.